Okay, so here's a relative motion problem. Uh, we have this wheel spinning around, and we have this link from B to C, and then we have C sliding down that slot. So the first thing to notice is that this slot here is not rotating. So this is not a rotating frame of reference problem, the ones with the Coriolis and the omega cross R plus what the camera sees and that sort of thing. So this is just a regular relative motion problem, which means we have V of C plus V of B plus V of C rotating about B. So before we go on, I just want to say a few words about these relative motion problems. There's always something that's spinning around a pin, typically in these problems. So you have something like this. And then you'll have that attached to something else. So the first thing I do when I do these problems is I look around for these pins that are fixed and are not moving, and then I know whatever's connected to that pin is spinning around there. And so let's say that's point A or that's point A, and this point out here is B, or that's B. And so in this case, you know that B is spinning around A because A is pinned and it's fixed. And so for velocity, for example, it would mean something like this. That would be the velocity at R omega. Okay, so you always look for something like that. And so as you look at this problem, it's pretty clear that that's the pinpoint at A. And so B is spinning around A. And we're given the alpha and the omega of this wheel. Okay, so back to the problem. We're going to do V of C is V of B plus V of C relative to B. You write that out, and again, these are vector equations. And so everything you know about V of C, well, it's going on that slot at 30 degrees. That slot's not rotating, so we know that V of C is inclined at 30 degrees. V of B. We've identified that B is spinning around A because A is pinned, and so the velocity of B is just R times omega. The R is 0.2, the omega is 6, so that's 1.2 meters per second, and perpendicular to that arm, so horizontal to the right because omega is clockwise. And V of C relative to B, that means C spinning around B. That's C relative to B. And this is interesting. We were given that the omega of BC is 0.8660 radians per second squared. That number looked familiar, and the more I thought about it, 0.8660 happens to be cosine of 30 degrees, and that will make this problem work out. But anyway, we know that C relative to B is going up, and it has that value. Well, this problem seems overspecified. The tangent of the y over the x had better be tangent of 30, or this problem's not going to work out. So the y component was this, the x component was that, and sure enough, it does equal tangent 30. So that works out. So it turns out we didn't have to do the velocity part. Typically, the omega would not be given, and you use this equation to get the omega. Okay, so now to the acceleration. Same thing. Again, vector equation. Sorry, A of C is A of B plus A of C relative to B. Again, A of C is along this 30-degree slot, so we know that A of C, it's going up or down. I figured out that it's going up. You can, if you're good at looking at pictures and looking at stuff, you can see it's going up the hill. But anyway, if you guessed it going down the hill, you would have gotten negative, and you knew that you guessed the direction wrong. Okay, acceleration of B. Again, we've identified that A is a fixed point, B is spinning around A, so it has a R alpha, perpendicular to that arm, and R again is 0.2, alpha is 3, so that's 0.6, and it has an R omega squared, always towards the center towards the point it's spinning around. So there you go, 0.2 times 6 squared. And then C relative to B, that means always C relative to B means C spinning around B. And so if it's spinning around B, there's a R alpha. So there it is, R alpha, and I've assumed alpha counterclockwise, so it's going up. And then you also have a R omega squared from C to B. We know that omega is 0.8660, that was given, or we could have solved it, and R is 0.8. So you have two unknowns here. You have alpha is unknown, and you have AC is unknown. You can just write out the two equations and solve for AC and alpha. If it were me, I would take the y component, and then then the x component. Well, let's see, what would I do? I'm sorry. Here's the unknown there. There's alpha. This actually is known. That's 0.6. So yeah, I would take the x component, and that would give me AC. And then once I know AC, then I would take the y component, and I would get alpha. So that's a simple relative motion problem. Simple, I mean, it doesn't have the rotating frame of reference. So